In this presentation, we'll look at some useful signal operations. And the very first of these that we should discuss is the summation of signals. So we're talking about what happens when we add, say, a signal x1 to a signal x2. We saw this in previous talks. And what I want to emphasize is the summation of signals means simply adding their values at each and every time. So to find the value of x at time 1, we take the value of x1 at time 1 and add to it the value of x2 at time 1. So consider the graph shown here at the bottom. I'm showing x1, x2, and then their summation, x. The second signal operation that we'll consider is time shifting. This is where a signal is delayed. So let's consider signal x of t here, and suppose it's being delayed by capital T seconds. We'll denote the result as phi of t. Now when we delay x of t by capital T seconds, that means we shift the entire curve over to the right by capital T units. It looks exactly the same as x of t, it's just now been moved farther to the right. Now mathematically, we can write this as phi of t is x of t minus capital T. That is, we replace small t by small t minus capital T. We can also consider a leftward shift in operating on our signal. As we take x of t and we produce phi of t by shifting the entire curve leftward. Now this is not a time delay, this is what's referred to as a time advance. Mathematically, we write phi of t is x of t plus capital T. That is, we replace each small t by a small t plus capital T. That's how we perform the time advance. Now I want you to note that both the time advance and the time delay, both kinds of time shifting, both of these are in fact systems in the sense that we stated from the very beginning of the course. A system takes one signal and operates on it to produce another signal. So time advancing or time delaying are in fact systems. So let's do a quick example. Let's consider the following signal. X of t is sine of t times u of t. Now I want you to note the special role of the unit step u of t in the creation of this signal. Since u of t is 0 for t less than 0 and 1 for t greater than 0, then the presence of u of t in the definition of x of t makes the signal 0 for t less than 0. It makes the signal the same as sine of t for t greater than 0. Now this particular kind of sine wave, one that does not begin until time 0, is referred to as a causal sine wave. We'll be studying more about this later. Now let's suppose we take this signal x of t and we delay it by pi over 2 seconds. So we'll shift the entire curve toward the right. Mathematically what we'll do is we'll replace each t in the definition of x of t by t minus pi over 2. So you can see that here at the bottom of the page. Phi of t is sine of t minus pi over 2 times u of t minus pi over 2. We have to replace the t in u of t by t minus pi over 2 to get the correct definition of this time-shifted signal. The next signal operation we'll examine is time scaling. In time scaling, we compress or expand the signal along the time axis. So for example, if x of t is the sawtooth that you see here in the graph at the top, and it extends between 0 and 3 seconds, if we do a time compression by a factor of 2, it becomes the lower graph, labeled phi. It now extends between 0 and 3/2. It looks just like the one above, except now it's been squeezed toward the origin. And that's an important fact to remember about time scaling. is that the expansion or compression is always done with respect to the origin in time. Now mathematically, the way we write this is we'll say phi of t is x of 2t. So to time compress the signal x, we simply take the argument t and replace it by 2t, in this case, for a compression of a factor of 2. So now let's look at time compression for a signal that is non-zero for both positive and negative values of time. Such signals are called non-causal signals. So here in this example you see x. It extends from -1 to 2 on the time axis, and it's that region where it has non-zero values. If we do a time compression by a factor of 2, the point at -1 will move to -1/2, and the point at 2 will move to 1. So if we time compress, again, we time compress toward the origin, symmetrically on both sides. Mathematically, the way we perform time compression is we take the signal and replace the argument t by at, where a is the compression factor and will be greater than 1. If we're doing time expansion, stretching the signal out, we'll replace t by t over a, where a is greater than 1, and this is the expansion factor. Let's look at an example where we do expansion of a sinusoid. We'll start with signal x of t, which is a sine wave at frequency omega. And I'll point out that this sine wave is non-zero for both positive and negative values of time. So this is not the causal sine wave that we saw before, where the sine function was being multiplied by u of t. Now we'll do a time expansion of this to find a new signal, and this time expansion will be by a factor of 3. Our new signal we'll call phi of t. So phi of t will be equal to sine omega t over 3. What we've done is we've taken the t and replaced it by t divided by 3, and we're dividing here because this is expansion of the signal, not the compression of it. Now, just doing a little algebra, we'll pull the division by 3 over onto the omega, and we'll note this is a new sine wave at a lower frequency. The frequency is now omega over 3. So our first signal, x, is shown here in the bottom left, and then our new signal after time expansion is shown below it. And you note it's at a lower frequency, a 3 times lower frequency than before. So here's a question as an exercise to see how well you're picking up the material we're going through in this class. Does time compression affect the power of a periodic signal? For example, sine omega t. When we time compress it or time expand it, will that change the power of the signal? The answer is no, and this is easy to show simply by doing the integration. Here are all the details. We have signal x, and then we time compress it to get signal z. And this shows the power of signal x is equal to the power of signal z. So now we'll move on to our last signal operation, and this is time reversal. In time reversal, we simply flip the signal around the origin on the time axis. So for example, if we look at x here, we see what looks like a step signal, except it starts at some positive value of time. Now after we perform time reversal, the signal is flipped around the axis. And now you see that it is non-zero at some values of negative time, but it's 0 for all values of positive time. Mathematically, we write phi of t is x of minus t. That is, we simply replace t by minus t where it appears. Now let's look at combined operations, and the question I want you to consider is whether it makes a difference what order we do operations in. This is the question of whether they commute. So let's consider an example. We'll look at the signal here that extends between -2 and 4 and is 0 for values of time less than -2 and for values of time greater than 4. And now we're going to consider two operations. One is compressing by a factor of 2, and then the other is delaying by 1 second. And on the left, you see when we do the compression first and then the time shift. And on the right, you see we do the shift first and then do the compression. And what I hope you see is at the end, we get different signals depending upon which operation we do first. So no, in these operations where we combine them together, they do not usually commute. It's important what order we do the operations in. In engineering, we do lots of linear operations. For example, we multiply by a constant, we take a derivative, we take an integral, and when we do these kinds of linear operations, they will commute with each other. However, when we're doing these signal operations here, they're in general not linear, and therefore they won't commute with each other. So we have to be very careful about the order of operation that we do. This is something we encounter in life all the time. If you're putting on your socks and putting on your shoes, the end result depends on what order you do these operations in. Let's now do some example problems to make sure you understand how to do combined operations. So our first problem, we have the signal x of t, and we want to find x of 1/2 t plus 1. We'll find the answer by two different methods. In the first, we'll time shift and then time scale. And in the second, we'll time scale and then time shift. In the first case, we'll shift first. So we'll write x of t plus 1, a shift by 1 second. So when we draw the diagram for that, we'll find x of t plus 1 is going to be a pulse starting at time -2 and ending at time 1. Then we'll do the time expansion. So we'll find x of 1/2 t plus 1. We'll expand the diagram by 2. So working from x of t plus 1, we will now expand out by a factor of 2 from t equals 0, and we'll find a new pulse which goes between -4 and 2 seconds. And this is our answer, x of 1/2 t plus 1. Now let's find the answer by doing the scaling first. So we'll now write x of 1/2 t plus 1 rather as x of 1/2 t plus 2 in parentheses. So this is showing the time scaling first. So first we'll find x of 1/2 t, and that will be a pulse between -2 and 4 seconds. Then we'll shift by 2 seconds. That will yield x of 1/2 t plus 1. So when we do that shift, we'll now get another pulse. And this one goes between -4 and 2 seconds, shifting toward the left because of the +2. That's our answer, and it's the same answer as before. Now let's look at the second example of combined operations. And in this example, we'll have a problem that has time reversal, time compression, and time shift operations. So we have given x of t, which looks like a sawtooth, and we want to find x of -2t plus 6. We'll write the argument -2t plus 6 as -2 times t minus 3. And by doing that, we can clearly show the different operations. The minus sign here, which I've labeled A, the 2, which I'll label B, and then the -3, which I'll label C. These are our three operations. A corresponds to time reversal, B corresponds to time compression, and C corresponds to time shift. We'll do the time reversal, operation A, first. So when we time reverse the sawtooth at the top of the page, x of t, we'll get a sawtooth, but this time pointing the other way, and it will extend between -4 and 2 seconds. Now that we have x of minus t, let's now do the time compression operation, operation b. So this compression is by a factor of 2, which means the whole waveform is going to be squeezed toward t equals 0 by a factor of 2, and that will give us x of minus 2t, which extends from minus 2 to plus 1. So now we'll perform our last operation, which is the time shift by 3 seconds. We have x of minus 2t shown at the bottom of the page. We'll now find x of minus 2 t minus 3 in parentheses. That is minus 2t plus 6. So we need to do a time shift by 3 seconds to our signal. That will take x of minus 2t and produce x of minus 2t plus 6. So graphing at the bottom of the page on the left, we'll take our x of minus 2t signal and we'll shift it over, shifting by 3 seconds. So now the signal extends between 1 and 4 seconds. And this now is our final answer. We found x of minus 2t plus 6.